So the reason we did all this, Heising stuff, actually, it's like almost like um, acrobatics, and the reason we did that is because we are playing a game of a special type. And when I mentioned that to you, that we're going to play a Steckelberg game in each period or in continuous time each instant. And notice in a control theory problem, we had a problem over time where we have to determine functions of time as control variables, but we changed the problem into a Hamiltonian maximization problem, where the Hamiltonian was maximized at each point in time. Given a lambda, we maximize the Hamiltonian at each point in time as if the future did not exist. So that idea carries over in the sense that now we should play the game at the Hamiltonian level. So when somebody says we play the game at the Hamiltonian level, it means we are playing an instantaneous game at each point in time. And that one is easy to do because at each point in time is a single period game and we know how to solve it. So there we go. How do we solve that? We define two Hamiltonians. This is the leader's Hamiltonian, manufacturer's Hamiltonian, and this is the retailer's Hamiltonian. Well, that's the objective function integrand. That's lambda m times the dynamics. And remember now, for this problem, I don't have, oh, I do have it. That's fine. So that's the Hamiltonian. And we're going to play the Hamiltonian level game. Notice that we don't need this term because our sigma coefficient does not depend on control. When that problem depends on control, the problem required a theory of differential equation, which is also more complicated. Okay, so most of the differential equation theory that we are using in the book, not most, all of it, we don't make sigma to be a function of u. Okay, so we don't need to put, since we're going to play Hamiltonian game, our variables are w and u, control variables are w and u, so we don't need to include sigma in the dynamics here. Okay, so this is fine. But the dynamics will be there through lambda m, because lambda m is the derivative of the value function, and the value function is going to okay. The value function is defined via a set of differential equations or partial differential equations, and the process x will still be stochastic process. So all of that will be there, but we don't need to worry about in the finding the u and the w at each point in time. But of course, but w as a function of x will depend on x, and x is a stochastic process. Okay, so that's what I mean by that. So to play the Hamiltonian game is like a news vendor. First, for any w that the leader will announce, which is the subsidy rate, I will maximize the Hamiltonian for that. This is the retailer's problem. Retailer is going to maximize the Hamiltonian for a given w. For a given w, I will take the derivative of that u with respect to h with respect to u. And of course, it will then be a function of x and a w. So we have a u star of xw, which is given by this. The leader will take, this is the response function. This is like the quantity being a function of wholesale price. But in single period problem, the state doesn't matter because it's fixed. But right now the state is going to change over time, so we need to put x in there as a function. Okay. So that's not there in the Newswender problem, in the single period Newswender problem. That one can be substituted in the manufacturer's Hamiltonian, just like a single period problem. He, manufacturer, to find W should take into account the response. So he's going to take that response into account and plug that into this formula. So I'm going to find the HM only in terms of W, because U is going to be response function, which is in a function of W right here. So I plug that in, all of that. And now I have a Hamiltonian. I put U star of XW here for U. I have only a function of W. Now I can maximize that function with respect to W by taking a first order condition. And I get this. See, if I take the derivative of this, set it to 0, I get Wx. Now, this is a slightly more complicated problem because that we know is positive, but that we want to be between 0 and 1. Now, here is how we break this and how we write this paper here. We know that this is going to be bigger than or equal to 1, no matter what. No, we know that this is not going to be bigger than or equal to 1 because it makes no intuitive sense. Because if I give you W bigger than 1, then the retailer will order an infinite amount of advertising. Cost him nothing. So there's no reason for him to order or advertise less than infinity. And so it's not going to happen. But it can be below 0. Because it is possible that the subsidy, it's possible that W can be below 0. And so we need to say W star equal to max of 0 and this. Okay, there's no subsidy rate going the other way. And so we have to solve the problem in two ways. Find the case where this is 0 and then solve that, and find the case when it is not 0 and solve that. And it turns out that we can find the case a priori. I can find that, so I can tell you what parameter will lead to this and what parameter will lead to this, and then we are done. So first we write the Hamilton-Jacobi-Bellman equation. But the Hamilton-Jacobi-Bellman equation will be two kinds. Because one will be V0 and one could be this. Any question?
Yes. Professor, why don't we set it as maximum of 1 at the expression there?
No, one is 100%. So the 100% is also not good because retailer will still advertise infinite amount. So it'll be strictly less than 1. So that is not going to happen.
Okay. Yeah.
But
thank you.
yeah, but what I'm trying to do is I'm not going to remember. I have to substitute this back into the Hamilton-Jacobi-Bellman equation, and I have to put lambda r as v sub x, the derivative of the value function, so that I have a partial differential equation. So I have to substitute this, and I have to substitute this. But which one do I substitute? Well, I substitute max, then I won't be able to solve the problem. But I know which cases will happen. So I can substitute this one time, and I substitute this another time, and I can solve two cases. So I can treat it as a case 1 and case 2. And each case, I can tell you a priori when it will arrive, depending on the parameter. Okay? Otherwise the problem becomes more difficult, but it is possible to do. So I substitute those guys in HJB equation. And right now I'm keeping that as, let me see now, what am I doing here? rho VR equal to this. I put V sub XR. And what I've done so far, I have left the W star X as W star X. So you can see I linked U star of X, W star X, V sub XR, and I just change the lambda M and lambda R into this. And if I can solve these, I will have the value function. So now I go into two parts. There is this part, and there is this part. And I have to investigate these cases. A, when it is 0, B, when it's positive, okay? So first, 0. No cooperative advertising. W star will be 0, so I insert W star 0 in this guys, in these two equations, and I get these two equations. First I solve for each, then I'll tell you, which one applies to under what parameters. So I have this. And once again, this is where we were not 100% certain that the linear value function would work. If linear value function doesn't work, we don't know how to solve the problem. But fortunately, it works. So we're going to solve this linear value function here. And then we can take the derivatives. And when we take the derivatives, we substitute that in these two equations. And then we substitute these and we equate the like powers of x on both sides. And then we can express all the unknowns in terms of beta. And I have then beta equal to this, beta m equal to in terms of beta, and alpha in terms of beta, and alpha m in terms of beta. So I can solve for beta, because that is a quadratic equation in this case. And then once I have the beta, I take the positive root. Once I have that, I can solve for all the other parameters. So this is very easy. This case is very easy, and we have a solution. Now, how to do the next step. So remember now, this is VXR is beta. That's, by the way, correction somewhere either in the slide or in the book. And we can write U star X in this form. And so the required condition is basically the following. I tell you this. The required condition is that 2 lambda m is bigger than lambda r. Because if if lambda r is bigger than 2 lambda m, then this quantity will become negative. So we want this quantity to be bigger than this quantity. Okay? And that means we want the derivative of the value function of the manufacturer and the derivative of the value function of the retailer must have some relationship. So we have 2 v sub xm is less than v sub xr, but we know that means exactly 2 beta m less than beta. Well, I know beta m and I know beta. So I write this. Notice now, this is original parameters. All of them are original parameters. So it tells me that if this is less than that, then W star is going to be 0. And so I redo this condition, and I redo this condition, I get this. It's the same condition as this one. But notice what's going on here. If you look at this equation, I define a theta, and I'm telling you when theta is less than 0, I won't give any subsidy. Notice what's going on. The rho and delta are small. Because this is a discount rate and this is that depreciation or attrition rate. So suppose I ignore this for a while. If I ignore this for a while, then the denominator here and denominator here are the same. That means pi m less than pi will give you W star equal to 0. What does that mean? That means that retailer's margin is bigger than the manufacturer's margin. What is going on here is manufacturer is saying, if retailer's margin from the sale is bigger than mine, then retailer will have his own incentive to advertise. Why should I help him? I don't need to help him. I don't need to subsidize. So this is it's an interesting result. It says if other guy's revenue is bigger for each unit of sale, then the other guy is not going to cringe and not going to short circuit his advertising effort. And so if he doesn't going to do that, why should I subsidize him? So he doesn't subsidize. So W star equal to 0 in this case. But of course, it's not exactly pi m less than pi. It is pi m less than something else. So that is a more precise condition. But you can sort of see that all it means is that if pi m is sufficiently, if pi is sufficiently larger than pi m, then there is no cooperative advertising. Now we do that W star bigger than 0. So we already solved the case. So now we know if this is not the case, then the other case must be there. So now we saying theta is strictly bigger than 0. If theta is strictly bigger than 0, then this is going to be the case. And if this is going to be the case, then W star x is going to be exactly this. There's no max 0 this. And I can substitute this guy into those equations, 2 equations, and I get the 2 equations now. So this is my new HJB equations. Once again, I do linear. When I do linear, now it's a little bit more difficult. Now I get 4 equations, which I cannot solve simply like this. Here I was able to solve beta, then all other in terms of beta. Here it is a little bit more complicated. So it is a lot more complicated to solve this. But if I keep substituting this, I get a cubic equation. I get a u star x, which is this formula. I get a cubic equation in beta when I manipulate these guys, and cubic equation can be solved. Okay, an Italian guy named Cardano solved the equation for the first time, and so we call them Cardan's solution. In English, we call it Cardan. In Italian, we call it Cardano. So we have a Cardano solution, which is, these are the 3 solutions. Now, these are another solution. These are the coefficients. So I'm going to apply the Cardano method. A1 is this one, A2 is this one, A3 is this one. So I have a cubic equation in these parameters, A1, A2, A3. And we know that A1 is bigger than 0, A2 is bigger than 0, A3 is less than 0 because there's negative. And now we can use some Descartes rule of sign, whatever, all of these things that we did in algebra course or algebraic equations, that exist a unique positive real root. And the 2 real roots may be both imaginary or both real or negative. That means there's only one positive root. Others can be either imaginary or negative. And if you do Mathematica, it will give you that. And if you have numbers, it will give you that. So I remember those 4 roots. That's what I meant by this. Here there are 3 roots. Cardan's solution gives you these roots. First root, second root, third root, where S and T are given by this, where Q and R are given by this. So you can see it's a long ways to go to parameters. The parameters are A1 equal to this, A2 equal to this, A3 equal to this. These are the parameters. And we can get A1, A2, A3 in terms of the parameters. Once you have A1, A2, A3, we can get Q and R. Once we have Q and R, we can get S and T. When we get S and T, we can get the solution. So the solution is written in this way. And it is completely clear, but it is a lot of notation to get there. And we all know which one is positive. It depends on parameters. Some parameter, this may be positive, and some other parameter, this may be positive. So we do not know. Okay. Remember, this is not necessarily a complex number, because that is I, but S minus T can also be imaginary. So I and another imaginary number can make it real. So So this is just the formula. This is imaginary number I, square root of minus 1. But we don't know a priori which one will be real, which one will be unreal. But if it's imaginary, they come in pair. So if one is imaginary, the other one will also be imaginary. Okay. So there's a lot going on here. In our paper, we said, but in case one, we can show that the positive root is this, the first one. In the case one, the first one is positive. In case two, there are three real roots with one positive root. So all three are real, even though there's I. This is also real, this is also real. But the first one is positive, and the other two are negative. Here, the first one is positive, the other one are imaginary, and they come as a pair. So there are the two pair imaginaries. Okay. Case three, S and T are both imaginary. So case T, actually S and T are imaginary, and we have three real roots and one positive root. But now we cannot tell you immediately which one. So we have subcases can be given to identify the positive root. For our purposes, it's enough to identify it numerically. So we now, it is possible to do more work here. It's probably there in the paper. But for this text, we just do numbers. So we can do numbers, and then we can find out which is positive. Okay, so that can be done. I now have the entire landscape here. When theta is less than 0, we know the value of theta for each case. Then this is the value function of the retailer, this is the value function of the manufacturer. These are the coefficients. So these coefficients are all known here. Subsidy rate is 0, and advertising rate is given by this formula. If theta is bigger than 0, then these are the value functions. Alpha, beta, and all of these are given by these four equations, which can be solved by using a cubic equation. Then we know that this is the subsidy rate. Subsidy rate is less than 1, and it is certainly not 0 anymore. And this is the advertising effort. So the entire landscape is clear in this table. And we can now do some numbers. So there are exercises you're asked to use these numbers. And then you do the number, you can find a chart for this number. You can see optimal subsidy rate. You see the retailer margin. As the retailer margin increases, the optimal subsidy rate is going down. You see manufacturer's margin. If the manufacturer's margin is increasing, then manufacturer has more interest in preserving his sales. So he is going to give more subsidy to the retailer. So as manufacturer margin increases, this subsidy rate goes up. So, yes.
Professor, I'm a little confused with these models.
Yeah.
So we have found the optimal W and the optimal control U star, and the value for the retailer and the manufacturer. How do we find, as in our assignment, um, the optimal market share over time?
Optimal share is negative?
No. How do we find optimal market share over time?
Yes. Oh, optimal market share over time. You find the optimal control, right? You find the
Yes.
optimal control, and you go and put the optimal control right here. Right here. Actually, even go further than that. Right here. You put
Yes.
U.
Okay.
And because W doesn't matter, all matters is U, right?
Yes.
For advertising, because W is only in terms of how you split the expenses. So you have the equation, and that can be solved using mathematical or MATLAB.
Oh.
That's how we did this, by the way. See, this is solved exactly the same way as this one.
So there is no explicit form for that, right?
Oh no, but we didn't put in the book because we already put this one in the book. This one is also a solution of this equation. See, this one is a solution of this equation. Use the control in this model, and then you go to this equation. This is more complicated equation. You can see that, right?
Yes.
Yeah, but you put those u1 and u2 in there, and you solve this equation, and that's what you get. This is, you can put that in Mathematica or MATLAB. They know how to solve the stochastic differential equation.
Okay, so we weren't able to solve this assignment without using a MATLAB or Mathematica.
No. You can solve that in some cases, but I'm not asking you to do that. I'm not requiring you to know so much about differential equations because that's another course all by itself.
Yeah,
So all the
you.
differential equations we solve are the one in appendix. That was very simple ones that we solve. But many times there's more complicated ones. You need to either go to, sometimes the Mathematica actually will solve the problem in closed form. For example, these roots, you can get in closed form. So you can get, if the solution is available in closed form, you can either do Mathematica or MATLAB, or you can go to handbooks of differential equation solutions and they'll give you the solution. So there are sources to get that. But if you were to write a paper, that's what you would do. In fact, we may have done some of that in the paper because we do quite a bit more in the paper than in the book. But for the numerical example, it's best to just use the software and do it. Did I answer your question?
Thank you. Yeah, perfectly. Thank you.
So now in the time we have, I want to do a few quick things. For all purposes, we finish here as far as the exam is concerned, okay? So what we now do is to tell you what else is going on, which is something interesting. The first thing I want to tell you is that a further extension of this, which we had a problem publishing in either marketing science or I think it's management science, because what we did was we said, what if manufacturers subsidize the retailer and the retailer subsidizes the manufacturer, and the manufacturer does the national advertising? So manufacturer does national advertising, and you have, let's say, two retailers. So the retailer are playing Nash game, manufacturer does the advertise, which helps both R1 and R2, and the R1 and R2 retailer, they do the local advertising in the local newspapers, for example. And the manufacturer does the national advertising, like, for example, dairy industry says, got milk, and they talk about just buy milk, drink milk, that kind of stuff. So national advertising that like General Motors, mark of excellence was an advertisement for the General Motors cars, but the different dealers get benefit of that. But they don't subsidize manufacturers' advertising. We said if you subsidize manufacturer advertising, you can gain, because if you cannot subsidize, then the subsidy is zero. So by allowing them to subsidize, you can only improve the objective function. You cannot go down. And you can then find cases in which that subsidy is required and optimal. So we wrote this whole paper, and we also did a lot of other things. But our journals are now saying, give us an example where manufacturer is subsidized by the retailer. And my argument to them was, okay, we don't have an example, but we can say that they should if they don't already. We can provide cases where they should and not. So what they're doing is not correct. It's not optimal. But that's not going to go. So, and also the referees were not very knowledgeable on stochastic differential games, so they did not know how to review the paper as well. So we sent it to a better journal in control theory, which is Siam Journal of Control, and that's the paper I told you is Ben Susan 2019. So that's an extension of this model where you can have a subsidy both ways. And that's where we also developed the verification theorem. So that is a direction that is already finished. The next one, let me see how much time we have. Yeah, so we have some time. So next one, I would, before we go to the next one, I like to give you a few stuff that I wanted to talk to you about. But before that, let me just mention that the next one again uses my model, SETI model, and we bring in a manufacturer, a retailer, and we provide a distributor in the middle, like a warehouse. So what we are now saying is the manufacturer sells the good to the distributor, and the distributor sells the good to the retailer. So now it is a 3 echelon game. And so you have a Steckelberg game where there's a leader, then there's another leader, and then there's a follower. So it's a stage-wise game, and that can be solved in single period, but we solve in continuous time. We use again the SETI model, and that paper went through one round. No, it went through one round, major revision, the second round, conditional acceptance, and the second round, they were asking us to do some thing that they did not, they thought we should give another example, so we did, and they gave us like 2 weeks to do it. We did like this in 3 or 4 days, and that paper was submitted last weekend, and it was accepted this week. So the 3 echelon paper has been accepted by PALM this week, and I will, if I have time, I think you have the paper, but I'm just telling you that we're developing different extensions of this and publishing in at least the one in PALM. We have 2 more papers along in SETI direction, SETI model. One is generalizing the SETI model called generalized SETI model, where instead of square root 1 minus x, we do 1 minus x to the power alpha or beta or whatever. And then we resolve the problem, and we are able to go quite far. That paper is right now sitting with the DE in OR, Operations Research, and we are hoping that the DE will accept it. But we are waiting for the DE to make his decision. The decision may come down to us, in the next 2 weeks. I decided not to ping the DE. I know him. He gave a seminar here, Gustavo Volcano, but I just let him be and decide whatever happens. So that's another one. I'm currently working on a paper with this one where we have another innovation where we can say the following. We have a market, but there is a exogenous process going on that's a Markov process, and that will switch them. It's a transition matrix, and you will know whether the market is good or market is bad. 2 states. So the market is good, G, market is bad, B. And at some time, market will switch from good to bad. And after bad, at some time, it will switch from bad to good. So that's a Markov chain. It is not under our control, but it is there. Okay. And I am now have my dynamics, which is different in good market and a bad market. And so there's a switching going on. It's called regime switching. And it turns out that we can generalize the SETI model to regime switching. That paper is finished. I'm actually going through that. I worked with the Hong Kong people in a math department there at Chinese U and another U there. There are 2 U's, two universities, and the 2 groups working with me. And that paper is ready, and I'm just going through the last version of that paper, and we will see where we send that. So this is kind of so far what is going on in terms of the SETI model and its extensions. Okay, now I'm going to go to Appendix D, point 8. Kushali, can you send me D.8?
Yes, Professor.
Or should I do it from my end?
Let me try it from my end. If it doesn't work.
Slides? Do you have slides? No.
No.
No. Then I can just do my end. It's easier.
Okay.
Yeah, let me just do my end. I have to open the book. Book. Here we go. D.8.
Page 460, 458 to 460.
Okay. So, in a couple of papers that I wrote, the idea was that if you have an initial state and you solve a control problem of infinite horizon, it goes to a stationary equilibrium, long-run stationary equilibrium. And the question now is, what if starting at a point it goes to equilibrium, and starting at another point it goes to a different equilibrium? And if in those cases maybe there's a point which we call indifference point, if you want to call it, that if you have that initial condition, then you can choose to go to that equilibrium or that equilibrium. Up to you, both are equally good in terms of the objective value function. Both give you an optimal solution, but the optimal solution is not unique, and the equilibrium is not unique. And I wrote that paper in 1977. And I just want to mention that the 78, another guy wrote a paper, Russian man named Skiba. And for some reason or another, I did not, as I told you, the paper was on the most rapid approach path, but I changed the terminology to nearest feasible path. And so that paper did not get picked up by the community, partly because of the keywords were not properly done. But anyway, those points got to be known as Skiba points until I pointed out to the powers that be, the people who are writing these papers, that I was actually had these points before Skiba. And so the community changed their name to DNSS point. Can you see the word here, DNSS? And some papers were written under this name, where D means Deckard Nishimura Seti Skiba. But that one got some papers published. There's a book that talks about this. There's a Wikipedia article on DNSS points. But now the people don't want to use that because it is not a very good terminology. And these guys never wrote papers, their papers for like 1980, so there's no reason for them to have names in there. So now some people are going back to Skiba point, and some people are also writing in their papers that the point should be called Seti Skiba points. I, of course, preferred the Seti Skiba point and not Skiba point. I met Skiba. Skiba wanted to meet me when I went to a conference 2 years ago in Montenegro, and so he told the conference people that he wants to see me because he knew I was going there. I never. So we met. We have a photo together. He was very happy to see me. But anyway, that's just part of the history, and I finally decided. So my papers are in real kind of problems. Skiba point also arise. The SETI Skiba point also arise in pandemic epidemic problem. I have an epidemic paper in which you also have these points, and then I will talk to you about the epidemic paper next. That is another one that we're going to do, and then that's kind of finish everything. So in epidemic point, there was SETI Skiba points, and so I wrote 2 or 3 papers on epidemic control in 1970s, and now they are being looked at again by people. Of course, they are very simple models of control theory, but now the epidemics are far more complex than those models. So the model that we we proposed, which is right now under second round in PALM. The version that you got is somewhere between the final version of the second round, but not the first round. So it's halfway or 3/4 of the way going to the final round. Okay, so it is not completely a final. So please do not distribute the paper. Just keep it to yourself, because we will put it on SSRN as soon as we submit the paper in the second round. And there, of course, it's a much more complicated model, and we cannot solve the problem, so we use numerical methods. Okay. So very simple example is given in this chapter, which is it's a made up example, not the examples of the real problem that I have in my papers, but that's good enough for the time being. So I have a problem 0 to infinity, this one, x dot equal to that. And if you look at phi and f in this example, so here's the example, and here's the x dot, and u is between -1 plus 1, you can do the following. If x0 is less than 0, I form the Hamiltonian. Lambda dot is given by this. U star is a bang-bang control. But x0 is less than 0, so the state equation, remember x here? So x is less than 0. So it gives x less than 0. And so it maximizes this product, and I get a long-range stationary equilibrium of -1, -1, and the lambda bar is negative. So this is negative, x is negative, and so this whole thing is negative, so control is -1. And I get long-range equilibrium -1, -1. So starting from 0, I will go down. So here is 0, I will go down like that. And I will settle down at -1. Okay, and lambda bar will settle down at -1, give the. Now, suppose I solve the problem with x0 bigger than or equal to 0. Then what happens is I will get 1, and I will settle down. So here's going like this. And if I go to positive value, it will go like that. So I have the different equilibrium. So if I'm already above 0, I will go above. If I'm already below 0, I'll go below. I have no choice. So that was what was happening when I did the 1977 paper. And I said, if that's what's happening, then by continuity, there has to be a point in the middle where I can go both ways. So that was the idea. The idea was that there must be a point that allows you to go this way or that way, and both are equal. So here you can easily see for x0 less than 0, I can go x0 bigger than 0, I can go up above. Then at 0, at x0 exactly at 0, I can choose to go this equilibrium or that equilibrium. Okay. So recently there's a paper that has been recently published, and some of the National Academy members are involved. Some of my colleagues in control theory are involved. And they recently published this paper. I don't have the reference for you. And they actually get a Seti-Skiba point, even more than a Seti-Skiba point. They get something called Seti-Skiba manifold. And there what they show is that in some cases, you can let the epidemic go unfettered, and that's your best solution. And in some cases, you kill the epidemic by social distancing or by vaccination or whatever. But there is a point in the middle where you can go that way and that way, depending on the initial condition. So that now is a bigger model where they actually have a more than one state equation, and they actually have a manifold. So it can be anywhere in this manifold, and you can go have many different solutions. Okay, so that is what's going on in terms of Seti-Skiba points. I'm hoping that more people write these papers and keep calling that, and one day maybe somebody or myself will change the DNSs to Seti-Skiba in Wikipedia. Hopefully that will be done. So are there any questions there? And then we're going to go to the epidemic paper that we currently have and currently working on. So there's a lot of control theory stuff. If you want to go in dynamic problems, then control theory is one way to do it. discrete or continuous doesn't matter, but 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 the name of the game has to be dynamic. So my research is generally speaking in dynamic and stochastic, and so does Ben Susan. So if you guys are interested in any one of these, you approach one or the other and see if you have some ideas. You can work on those problems. There are some interesting problems to look at, and as you can see, they can be published. Oh, this is a guy who's a member of National Academy, and the new paper is involving John Calkins that I just mentioned to you, that they have a Sethi schema points. But in their paper, they call it schema points, but in the text, they say that these points are also known as DNSS point and Sethi schema points. So they at least do some lip service to this terminology. I am a little bit disappointed because these are my friends and they should push the name which is appropriate, but that's that. Okay, so if there are any questions here, I'm going to switch to the epidemic paper that Kushali has slides. Oh, I have slides. No, I have slides. So I'm going to go through myself. Are there any questions here before I move to the next topic? That is the topic of much more current interest. So let me just go there. Where are the slides? There are the slides right there. I don't want to edit. I just want to go like this. So this paper is written as control of an epidemic with endogenous treatment capability under popular discontent and social fatigue. And it's a co-authored by Fouad, who's a professor in France, and Eugene Kamlitsky, who's a professor in Israel. And this guy is doing most of the numerical work for us. I'm doing most of the theoretical work, and Fuad is doing most of the writing. But the writing is a little bit too wordy. The French people write just too many words. So I don't know how, but I'm going to spend some time trying to whittle it down to some level. Okay. So the idea is that the new idea that we have in a control theory formulation is what is called a social fatigue. And that is actually quite important now. If you look at in India, there was everybody was very complacent because there were very few cases, and they decided to remove all the beds and facilities that built up, and now all of a sudden the second wave is just killing them. In the United States, for example, now there is a social fatigue of people not wearing masks, and people become, I remember that I used to wash my hands exactly 30 seconds or more for the entire year, but now when I wash my hands, I actually don't spend 30 seconds, I maybe spend only 15 seconds. But partly because I feel that I'm double vaccinated, and so I can take a little bit less precaution as I did. But once again, I'm not going everywhere. I'm not going to travel. That's a social fatigue in action. I only gone to doctor yesterday, my physical, that was nicely done. Going to dentist next month. But these are the first events I'm doing going inside a grocery store. Only 2 times in the last 14 months I gone to grocery store, inside a store only 2 times. So let's look at what's going on. I'm going to go quickly to the model, and we don't have so much time, and I just want to give you some feeling for what is going on. And these kind of models I'll call SIR model, SIR model. SIR model are model where S means susceptible, I means infected, and R means recovered. But those models are very simple. If you look at my 1977 papers, there are some references. I'll show you the references later if I mean, you have the paper. You have the paper, and you can see that the 2 or 3 papers cited are my old papers, which are very simple compared to this chart here. But this is a more complicated SIR model. So in this model, these are the susceptibles. We start with AT. AT is the number of people, total number of people. And these are kind of infected people. And if you subtract those 2 guys from that guy, that will be ST. ST will be susceptible. I'm going to put ST in there because we want to at least connect it with this shear model. Fuad is refusing to do that because he likes this, but I prefer that it's better to have a more connection with the literature. And that would be changed to I1, which is infected of type 1, which is asymptomatic. And that is going to be changed to I2, which is asymptomatic. And that's going to be changed to I3, which is recovering. And that's going to be changed to R, which is recovered. Okay, so that's how the model goes. We start with susceptible. And susceptible at the rate of alpha goes and become infected. Okay, so they all become asymptomatic in the beginning. Okay, they affect all of these and they become this. And then asymptomatic, some portion of that becomes symptomatic. And some portion goes this way, and some of them, and a portion of that become recover because they recover, asymptomatic people recover, and some people relapse and recover but not susceptible, and some people become susceptible. So there are parameters. You can see ADA, psi, and all this. This is a model without any control. Okay, this is a SIR model which only tells you how the world goes, how the world will evolve. Some of these become symptomatic, and we allow the death only in the symptomatic, so some people will die. And some people will go into treatment. Once they go into treatment, some people will relapse and go back to symptomatic. Some people will recover, but after they recover, some people become completely immune, so resilient, and some people will go back to susceptible. So this is our model. Given this model, these are the differential equations. Remember, you need A1, A2, A3, and that's enough. You don't need that because that's coming from there. So we have A dot, there is some decay, then these are going to different boxes. So the shear model is like a compartmental model, and different compartments, they go to different compartments. You can see A1 dot is alpha times all of these guys, alpha times sigma times the susceptible. Okay, so sigma of all these are infected, they interact with people who are susceptible. So we are saying every one of these people interact with these guys, and the infectivity rate is alpha. So alpha is the rate at which so social interaction can remove that interaction, right? You can reduce the alpha by putting some social interaction. Okay, and so this is the equations, beginning with the equation, and we try to solve the problem without any control. And then we solve the problem with control. So when you use the control, and we collect some data, and we also compute what is called R0, which gives you the herd immunity. So R0 in our model is roughly between 54% and 70%. I have site references how to compute R0. They require kind of matrix inversions and stuff like that to get to R0. The model R0 depends on all of these parameters and the compartments. So in each case, you have to compute it. There's a mathematical formula for that. And then we go to the next stage. I'm just going to give you quickly, and we put controls. You can see when we put a control, and we can reduce the rate alpha. So alpha 1 minus this, and we can, so some of the controls we call mobility restriction, which means lockdown. The other control we call social securing social interaction, that's social distancing. So we have mobility, we have lockdown, and social distancing. Those are the two controls. So we examine the model with only social distancing. We examine the model only lockdown, and we examine the model where you can do both. You can do some lockdown, some social distancing over time. These are, of course, you have to optimize them. So once we have the controlled model, then we have to come with objective functions. So we have you see here the costs are being talked about, various costs which are quadratic because we want to solve the problem. So we have objective functions here. So we want to minimize over these controls. These are the cost, and you can see the discount rate is the way by which we give you social fatigue. Okay, so we can have a negative discount rate to do the social fatigue. And so we can see some parameters somewhere. I don't know where these are, but Fuad just presented this paper in Palm Conference a few days ago. So you can see the social discounting here gives you the fatigue is coming into this in some way. And then we do various solutions with the optimal control and do the numerical ones and chart various charts or whatever going on. And we finally give conclusions. Okay, so that's kind of, I'm not going to get into the details of this because this is a control theory course, and I just want to tell you that we cannot solve the problem, but numerically we can draw some nice looking pictures and come up with some prescriptions. So this paper was written, first draft of this paper was written when we knew that vaccine is not around the corner, that the vaccine will take at least a couple of years, and we don't have so much time. So we need to do social distancing and mobility restrictions. But the vaccine came rather quickly. This mRNA vaccine platform is a completely new phenomena, and it saved the day in some sense. But we did not put vaccine in a model because that's going to change the whole thing altogether. Because then you have to have the control called vaccine. Then we have to put people who don't want to be vaccinated, and we have to put age groups, and so it's become more complicated. Okay, and that would be a new paper in any case. So our paper is not coronavirus paper. It's for any pandemic or any epidemic, not even pandemic. And coronavirus is an example where we collect some data and give some graphs. So the paper is more general in that sense. In some cases, vaccines are not available anyway. And so we are assuming that the epidemic that we are dealing with are epidemic without the vaccine possibility. So that's all I have to say. We got a few minutes, so I would open the floor for questions if there are any questions. And then we will exam next week, right?
I already sent out the details, so the time for 10 a.m. is approved by the dean's office. So it's from 10 to 12:45. It's closed book, just like last time. Only one page of notes, one side, only 8.5 by 11. No calculators, no cell phone, no other materials allowed. And it's from chapters 6 through 13. There'll be 4 questions, and each question is 10 points.
Yeah,
and you need a working web camera and a microphone. And then at the end, you have to switch off the phone the whole time, and at the end you can turn it on to scan your exam like last time, just like midterm.
Any questions regarding that?
Oh, I also had a few questions. This doesn't apply to the IS students. This applies to the OM students. I had received few requests of asking me questions about the qualifier exam. So the qualifier exam, this is different than the final exam. This is qualifier exam. So the qualifier exam, you have to know all the 13 chapters. There'll be only one question. There are no notes. There are no notes allowed on the qualifier exam, and you have to come up with stuff on your own. If it's like pretty complicated and if we feel there's a need for a hint, then we will provide the hint, but only if it's needed in a very complicated case. Otherwise, you're expected to know everything.
Yes, what I do is I do provide you a hint if it's a if it's a if it's a like a complicated fourth chapter maximum principle or something like that. But you are supposed to know at least the first three chapters to know what the maximum principle is. Anything that is somewhat complicated, I will provide that formula in. Okay, so that's kind of the
So
way it has
just to
been.
be clear, no notes at all for qualified exam and 1 page of notes, one side only for final exam.